Hello, viewers. Welcome to yet another tutorial class with Mr. Uche. Today, I'll be taking you in on the topic Newton's laws of motion and linear momentum 1. Remember, my first tutorial class with you was on fundamentals of motion, and from there we looked at the classification of the study of motion, which is kinematics and dynamics. And I emphasize on kinematics, which is the study of motion without involving the force that causes what motion. But today I will be taking on an important topic under what dynamics, which is Newton's laws of motion. Okay, and before we continue into these laws, let us quickly look at the objectives for this lesson. Okay, learning objectives. By the end of the lessons, I would expect my students to state the first law of to state the Newton's first law of motion. 2, to explain the concept of inertia and how it is related to Newton's first law of motion. 3, to give practical examples of Newton's first law of motion. 4, I would expect them to state Newton's second law of motion, and more importantly, to derive the formula of Newton's second law of motion, which is F equal ma. Then number 6, I expect my students to be able to solve practical problems involving Newton's second law of motion. Then we now move into Newton's third law of motion, and I expect my students to be able to state the laws, to state practical application of Newton's third law of motion, and as well as solve questions that has to do with Newton's third law of motion. Now, having listed the learning objectives, let's now move into the business of today. Now, the first aspect we have here is Newton's first law of motion. Okay, before we state the law, let us look at this diagram of what we have here. Look at this object that is placed here. The object is at rest, of course. It is not moving. Okay, look at pillar diagram 2. We have two men of equal forces pushing at both ends of the object. Mr. A is pushing from this end, while Mr. B is pushing from this other end. And both of them are applying equal magnitude of force. And what happens to the object? The object is still maintain its state of rest. Okay, let's now have Mr. A coming over to join Mr. B, as we have in the third diagram. A and B applying the same equal forces, okay, combined forces here, and exerting it on the object B. What do you expect in this situation? Now, of course, the object will start moving. So what do we mean in this case? This object was at rest and will forever continue to remain in this particular state. Okay? This particular object too, though we have forces on both ends, but the forces on both ends are equal. So the net forces acting on this object is 0. So at this point, the object, of course, still remains at rest, despite the fact that forces acting on it are acting on it. But then the forces acting on it, the net force is equal to 0. But coming to this point here, forces acting on it are on one end. Of course, you have some forces here, which I will refer as the air resistance. Okay, they are acting on this point, and of course, maybe frictional force. But the forces at this particular end are greater. So as it is being applied, of course, the object begins to move. Same goes with the ball we have here. The ball is at rest, and this ball will continue to remain in this position. But then this young footballer comes, kicks the ball, applying a force on it, and there is the uniform motion of this ball. But at the end of the day, this ball is being stopped by the net, of which this ball might continue this particular state of motion if not for this one net. But at least for a while it will continue moving ahead. If not for this one net that we have to hold it. So the net is being seen as an external force that stops the ball from moving forward. So all these are good illustration of Newton's first law of motion, which simply states that every body or object continues in a state of rest or of uniform motion in a straight line, unless when it is being applied by a net external force. Every body, every object that is at rest or that is moving in a uniform motion along a straight line will continue in that state of rest unless a net external force is acted upon by that rod on the body. Okay, now to discuss more on to go further to discuss on Newton's first law, we need to understand a very important concept, which is inertia. The inertia. When you say the inertia of a body, when you say inertia, what does it simply means? Okay, let's look at an instance here. We have two boys, okay, in this case, two boys. One, okay, of large mass, maybe a fat boy, then the other one is slim boy, and they are both seated. And I want to know either of the boys who among them is going to stand up very fast at the count of 2. Now when I say 1, 2, stand up. Now to you, whom do you think that is going to stand up first? Is it the fat boy or is it the slim boy? Of course, the answer should be that the slim boy will stand up faster. But the question there is that why is that the slim boy stands up very fast, very quickly than the fat boy? Now the fat boy, being seated, has a greater mass, a very large mass. Being seated, he has the tendency to remain in that particular position, meaning that the reluctantness for the boy to stand up is very low, or the tendency for him to keep sitting down is very high. Reason being that the boy has a large mass. Then what about the slim boy? He stood up very quickly. Reason being that the tendency for him to remain in that state of sitting position is so small. So he stood up very quickly. Meaning that the mass of a body has a very good relationship with the inertia of a body. So the mass can be used to determine the inertia of a body. But then, what is inertia? The inertia is the tendency of a body to remain in a state of rest or of uniform motion in a straight line unless a net external force acts on it. Inertia is inherent to a body. It is the property of a mass, or a matter rather, but mass is a measure of the inertia of a body, meaning that if a body or an object has a greater mass or is more massive, it means that the object will have a greater inertia. So we can simply say that there is a link between this concept of inertia and Newton's first law of motion. So most often we relate Newton's first law of motion as law of inertia. Both of them have to do with a body remaining at rest or a body remaining in a state of position, or when it is moving at a uniform speed along a straight line, unless an external force is applied on that body. Now let's look at some of the examples on inertia. Okay, some of example. First, let's quickly look at this particular this other example we have here. Here we have a glass cup, then here we have a cardboard, and on it we have a coin. Normally, if you should draw this cardboard, okay, just draw it, reluctantly. Perhaps the coin would go off with the cardboard. But if you draw it quickly, just draw it quickly, you are going to experience something else. You experience that the coin will drop into the cup, just as you have here. But then what is the reason of this? It is not magic, but it is real. And what is the effect of this? It's as a result of the inertia of the coin. At this particular point here, the nature of the coin maintains its state of rest at this particular point. So immediately you draw it, what happens? The coin remains in a state of rest at that point. Then gravity acts on the coin, which makes it to now fall down. The same thing happens to what? To the hammer we have here. Okay, most times when carpenters work and they find that the head of the hammer is what? Is a bit loosed up. So they tend to hit it on the what? On the ground or a hard platform, so that the head can get tightened to the handle. Now what they do, they don't understand, but what is being applied there is what? Is the law of inertia. Now this metal you have here, the head of this metal, tend to remain at rest. But when you hit this particular point, the body tends to remain in a state of rest, but then acted upon by what? Gravity down here, which pulls it down, and the reaction force of this handle pulls it in, thereby creating a tight situation, a tight situation here of the head of the hammer with the handle. All right. So, having said that, before we now move into the next aspect, of Newton's second law, let's quickly talk about the applications of Newton's first law of motion. Some of the application, day-to-day application of Newton's first law. Okay, this can also be related to the application of the law of inertia. Okay. Okay, let's look at the driver we have here. This man driving. As he's driving down, you know that the man himself has also attained a speed which is equal to the speed of the car. So as the body is moving, he's moving with the same speed of the car. Now let's assume that he sees an obstacle in front of him and step on the brake suddenly. What do you think should happen to this man, or what do you think should happen? Okay, the man can go off. He will tend to continue the state of motion. The speed of the car which he has already attained, he will tend to continue that speed. So if he has a seat belt, what happens? The seat belt will have to pull him back. But if he doesn't have a seat belt, wow, so sorry, it's going to be very, very very grievous. It's either the man hits his head on the steering or on the dashboard, or perhaps even worse still, can even go destroy the windscreen of the vehicle and go over. So as a result of Newton's law of motion, the driver was in motion, which has attained motion of the vehicle, and on stepping on the brake, he jerks forward. So this is also seen as in the case of headrest that we have in the car. Yes, the headrest we have in the car is not just for fancy. Now when you sit down and the driver tends to start up the car and press on the accelerator, immediately the car jerks forward. You tend to jerk backward, and because of the headrest, your neck does not go far backward with such opposite speed or acceleration. So the headrest you have there will definitely hold you so that you don't injure yourself. All right. So let's move on to before we go into this Newton's second law of motion, let us quickly look at a concept that will enable us to understand the Newton's second law of motion. Without this particular concept, it will be a bit difficult for us to understand the Newton's second law of motion. And the concept is momentum. What is momentum? Momentum of a body is defined as the product of the mass of the body and the velocity of that same body. Momentum of a body is defined as the product of the mass of the body and the velocity of the same body. So momentum mathematically is mass of that body times the velocity of that body. It is represented with a low key p equal mv. And what is the SI unit for momentum? The SI unit for momentum is Newton seconds. Okay, actually from derivation it is kilogram meter per second, but it is equivalent to Newton per second. This we are going to see in the subsequent slide why it is Newton per second. And of course, momentum is a vector quantity. How then do we know that momentum is a vector quantity? Remember in our last class in mechanics, when we discussed about scalar and vector, I did give you a kind of rule which you should be able to identify scalar and identify vector. Okay, so the rule simply is that when you have scalar, of course the quantity will definitely be scalar. But when you have scalar vector, the quantity would be the vector. So looking at the definition of momentum, we have mass times velocity. Mass is is a scalar quantity, while velocity is a vector quantity. So then we have scalar times vector. So scalar times vector will now give us will give us vector. It's just like when you say minus times plus, we give you minus. The plus gives you the same word gives you plus. The minus gives you plus. Okay, so that is it. So a little calculation here on momentum. The question says a body of mass 3.0 kilogram moves with a velocity 10 meters per second. Calculate its momentum. So quickly, the first thing you need to do is to write out your parameters. So guys, I would like you to quickly write out your parameters and do the solution. So what then do we have? Okay, given parameters, m equal 3.0 kilogram, v your velocity equal 10 meters per second. Then what then is the momentum? Mass times velocity. 3 times 10, which is 30 kilogram meter per second. Very easy, right? Okay, now let's dive into the very important law, that is Newton's second law of motion. Okay, and from this Newton's second law of motion, we are going to find out how a very important formula in physics is being derived. A very useful formula that is very, very common, and that is F equal ma, force equal mass times acceleration. Okay, so Newton's second law of motion. The Newton's second law of motion states that the rate of change of momentum with time is proportional to the applied force and takes place in the direction of the force. Let's take that again. Newton's second law of motion states that the rate of change of momentum with time is proportional to the applied force and takes place in the direction of the force. Okay, in the direction of the force. So this simply tells us that that momentum itself is a vector because it moves in the direction of the force. Okay, so let us look at the mathematical expression of what we have here. That the force is directly proportional to the change in momentum. So this is the change in momentum, and over time, the rate of change in momentum with time. So this is how it is expressed mathematically. Okay, F proportionality sign here. Then change. This symbol here means change. Delta means change. Change in what? In momentum. This is the symbol for momentum. All over T. So if we say change in momentum, it means that we have the final momentum and we have the initial momentum. So remember, in our kinematics, we established that we have, for a body to move with a uniform acceleration, it starts or begins from an initial velocity and attains a final and that velocity, which is the final velocity. So we have two velocity in this case, initial velocity and final velocity. So v is the final velocity while u is the initial velocity. So since momentum is the product of of mass and velocity, so it means that my initial momentum will be mass times the initial velocity, while the final momentum would be mass times the final velocity. So when you want to have a change in momentum, so you now say the final momentum minus the initial momentum. The final momentum mv minus the initial momentum, which is mu, all over time. So what happens here? Of course, we know what factorization is. So we factorize the expression here, change in momentum, to have what? M into V minus U. Why? Because M is common. So we factorize here over T. Then still a recall of one of the equations we had from the definition of acceleration, which is the rate of change in what? In velocity with time. So this is the change in velocity, V minus U all over T. So this is acceleration. So what happened there? We simply substituted V minus U over T for A. Okay? And we now have it here, MA. So V minus U over T is A, which I've just substituted right here to have here. Then when you equate this, I introduce my what? Constant of proportionality, K, which is always what? 1. Okay? Then F is equal what? MA. Okay. So let's move now to the next slide and see. Of course, force is measured in Newton. And what then is Newton? Fine, you might be asked to define Newton. Definition of Newton is different from definition of force. So what then is Newton? Although you can define Newton when you look at what definition of force, which is M mass times acceleration. So Newton is defined as the force that produces an acceleration of 1 meter per second squared when it acts on what? On a mass of 1 kilogram. Newton, once again, is defined as the force. Okay, let's add this. It's defined as the force of 1 Newton. Yes, it's defined as the force of 1 Newton that produces an acceleration of 1 meter per second squared when it acts on a mass of 1 kilogram. So the definition is based on Newton's second law of motion. So let's see some other things which we can deduce from this Newton's second law of motion. As we have here, we have another important concept here again that we can deduce from what? Newton's second law of motion. Now from Newton's second law of motion, as I explained earlier, force proportional to what? Rate of change in momentum with time. So this is the change in momentum, final momentum minus the initial momentum, and this is what we have here. So where K is a constant of proportionality, which is equal 1, so we now have F equal what? MV minus MU all over T. So when you cross multiply, we now have Ft equal MV minus MU. Now, what is the product of force times time? The product of force and time. The product of force and time gives us another important physical quantity in the study of what? Of motion with respect to the force that causes it. That is in dynamics. And what is this physical quantity? It is referred as what? As impulse. So if you are asked to define impulse, impulse is the product of the applied force or the impact force and the what? And the time or the impact what? Time. Alright. Now the impulse also have another definition. If you look at this, Ft, force times time, is equal to mv minus mu. This is change momentum. So it means that if I don't want to define impulse as the product of force and time, I can define it as what? The change in momentum of a body. The change in momentum of a body. So let me bring this to your understanding that in this case, the momentum of the object, both the initial and the final, are in the same what? Direction. The change momentum is in the same what? Direction. Okay, so that means that we can also have a change in direction when when the velocity changes and it moves in opposite what? Direction. So when it moves in opposite direction, something happens here. And what is that? Now this one goes forward, positive, while this one comes backward. So it's going to have a negative what? Sign, minus mu. So we will now have mv minus mu. We will now have mv plus mu. mv plus mu. So this is used in a situation where the velocity or the momentum changes its direction opposite to the direction where it was going before. So we are going to see some questions that is attached to this, how it is being solved. But in the case of what we have here, the momentum is in the same direction. the change in momentum is in the same direction. And of course, when you have momentum in the same direction, there's going to be a loss in momentum. But when you have it in the opposite direction, there's going to be a gain in momentum. All right. Impulse, as I've defined earlier, is the product of the net force acting on the body and the time during which it acts. So the impulse is force times time, okay, which is given here, and the SI unit is Newton seconds. So it means that, so if impulse is equal to the product of force and time, and as well as what the change in momentum, and the unit for change in momentum is kilogram meter per second. So it also means that since impulse is equal to force times time and change in momentum, they can still share the same word or have the same unit as Newton per second. So if you have moment being described as, whose unit is being described as Newton seconds, it's as a result of impulse, which is equal to force times time and as well as the change in momentum. So impulse. So guys, check this out. Is impulse a scalar or a vector? Let us confirm this quickly. So force is a vector and time is scalar. So we have vector, scalar. So definitely impulse is a vector with quantity. Okay. So a quick example on this. A quick example on impulse, force, and change in momentum. The first question here says a net force of magnitude 0.6 acts on a body of mass 40 gram initially at rest. Calculate the magnitude of the resulting acceleration. Okay, let's get our parameters quickly on this. Okay, parameters, guys, quickly. All right, so let's see how the solution goes. Now, having taken your parameters, the force, magnitude of the force is 0.6 Newton. The mass is what? 40 gram. But gram is not the SI unit, so we need to convert the SI unit of gram to what? To kilogram. And we are to look for what? Acceleration. So what comes to your mind looking at the parameters F, M, A? So what comes to your mind? Force is equal mass times what? Acceleration. So guys, we key in the value, the figures. When you substitute, here we have A, divide both sides by 0.04, and our final answer is 15 meters per second watt square. So that is our acceleration. Next question here says a truck of mass what? 3,200 kilograms moving with a velocity of 10 meters per second increases its velocity to 20 meters per second in 5 seconds. Calculate the magnitude of the force exerted on the engine. First thing we need to do is to have our parameters. The mass is 3,200 kilograms. Remember, the object was moving with a velocity of 10 meters per second, then attained a speed of 20 meters per second. Then we have our time in 5 seconds. So we are looking for the force. So F, M, U, V are all given. Okay, they are all the variables that we have here. So what formula has all these variables? So we now key into F equal mass into V minus U all over T. So plug in these values and solve. Subtract 20 minus 10 gives you 10. Then when you solve, finally we have our 6,400 Newton. Okay, and that question here we have a stationary body is hit by an average force of 15 Newton for a time of 0.03 seconds. What is the impulse experienced by the body? So I give you 3 seconds to quickly. Okay, let us say 10 seconds quickly. 10 seconds. All right. So let's check our answer. So here we have the force 15 Newton. We have the time 0.03 seconds. Then the impulse from what we have here, the formula suitable to use for this is what? Force times time. So when we key in the figures in there, we have our final answer as 1.5 Newton watt seconds. Next question says a car of mass 200 kilogram moving with a speed of 30 meters per second was suddenly hit by another car, okay, moving in the same direction. What is the impulse received by the first car if the speed attained at the time of impact is twice the initial speed. Let's take note of this. It says that what is the impulse received by the first car if the speed attained at the time of impact is twice its initial speed? Okay, meaning that if the initial speed is 30 meters per second, then the final speed was reached as what, twice of the initial. So we are going to have 2 times what, 30 to give us 60 meters per second, which is the initial what, which is the final what, velocity. So the mass is given. So from what we have here, how do we obtain our impulse? Remember that impulse, being the product of force and time, is also referred as the change in momentum. And what is this change in momentum? mv minus mu equal, when you factorize, m into v minus u. So when you plug in your figures in here, solve for it, 60 minus 30, we have 200 times what, 30, to give us what, 6,000 Newton seconds. But you can as well just, substitute your values here directly, you still have the same answer. Anyway, you have the same answer. Alright, next example we have here. A ball of mass 5.0 kilogram hits a smooth vertical wall normally with a speed of 2 meters per second and rebounds with the same speed. I love this. And rebounds, yes. This takes us to a situation where we have the velocity moving in opposite direction. Now, before we solve this, there are 2 ways you can reason this out. Your velocity, the initial velocity moving in a particular direction, okay, then rebounds, then start coming. So maybe a vector is in the opposite direction, it takes the sign of negative. So you have that the final coming to the opposite direction is negative. So when you have the negative of the final minus the negative of the initial, so after solving at the long run, the momentum will take the sign of negative value, telling us that it was the object is moving in the opposite direction. The momentum is in the opposite direction. But at the same time, you can have it the other way around, that your v minus your u, then take the u, since it is the same value or magnitude, or even if it's not the same value or magnitude, as long as it is coming opposite, it takes its negative sign. So v minus u will now give us v plus u. So there are 2 ways of working this out. It's either you say what, minus v minus u, such that the overall answer, the momentum, will now become what, negative value, or you say what, v minus u, that means it's coming in opposite direction. So we now have v plus u. So let us see what is being used here in solving this question. Okay, now I have that the mass is given, u is given, then v is coming after making that rebounds on the wall, now moves in the opposite direction. Since it is moving in opposite direction, that is a negative sign. So let us substitute into this, change the momentum, m into v minus u. So I have my v, which is negative, then u, which is negative. So when I solve, at the long run, I have a negative sign, which tells me that it is moving in the direction of the final velocity. The magnitude of impulse is 20 nanoseconds, but the direction is in the direction of the velocity, or of the final velocity. Okay, or it can also be in the direction of the greater velocity, or the velocity with a greater magnitude. All right, so you can see I have this as a plus sign when it comes to the case of rebounds, in the sense that the velocity v minus, then you are taking the u to move in the opposite direction to the v, which is minus u. So minus gives you plus. So in this case, you are going to have a magnitude of of momentum, but then it will move in the direction of the velocity of the greater magnitude of the momentum. Okay. Another question. Okay, this is not another question. All right. Okay, let's now move to the application of impulse. It's either you term it to be the application of impulse, or you term it to be the application of Newton's second law of motion. Okay, we can see this. Okay, let's have this man here, the driver here. So you can see what happened to the driver here. Perhaps he must have collided with an obstacle. Okay, that is why we have this airbag that is being what produced here. Okay, so imagine if there is no airbag, what do you think would have happened to this man? Oh, of course he would have had a damaged what face. Okay, because you have the head, we collide with the steering or with the dashboard, or perhaps straight to the what windscreen. Okay, maybe not the windscreen, because he has what he has a seat belt here, which will definitely bring it back. You can remember the Newton's first law of what of motion. Okay, but what are we saying here? Why do we have this airbag here? Okay, now let us go back to what we discussed under what Newton's second law of motion. Let's quickly just go back and have it then before we now come back to look at the application. So guys, let's look at these aspects. Okay, look at the relationship between force and time here. Relationship between force and time. What does it tell us here? It simply tells us that if we have a prolonged time, okay, when there's an impact, so if there is a prolonged impact time, it means that the impact force is going to be what? It's going to be less, be reduced. But if you have a less impact time, that is a short impact time, that means that we are going to have a greater what impact what force. Now this relationship is very much important when it comes to what application of impulse or application of Newton's second law of motion. So we use this relationship to explain or to interpret the application of Newton's second law of motion. So let's go back and see the application, what we have there, for further explanation. Okay, so right here we have this. So why did we have this airbag? Now this airbag, really there's a collision. The man that has already attained the speed of the vehicle moves forward as if he intends to continue with that same motion. Okay, but the saving grace is that we have an airbag here. So the purpose of this airbag is that as the man goes in, he goes deep, presses in, so there is a prolonged contact between the man and the airbag. So since there is a prolonged contact between the man and the airbag, which is the impact time. So there is a prolonged impact time between the man and the airbag, which means that the impact force is going to be what? It's going to be less. So if the impact force is going to be less or is going to be reduced, it means that the damage or the harm that will cause to the man will be reduced. So prolonged impact time will lead to reduction or shortening of the impact force, which will eventually reduce the damage on the object or anybody. Coming to this again, the same thing occurs here in this helmet. Okay, the cyclist helmet. Now if you look inside this beautiful helmet, you see that it is being padded. We have foams that is being padded around here. Those foams are not actually for fancy. They perform the same function of this airbag. So when the person falls down, the impact the foam causes a prolonged or increases the impact time. So when the impact time is increased, the impact force is shortened or is being reduced, so as to create a reduced damage to the cyclist. So here we have the bumper as well, the bumper of cars. Fine, they are not created just for beauty anyway, but they have a major purpose. And what is that purpose again? The purpose being that when a vehicle comes behind, collide with it, okay, it goes in, creating a prolonged impact time. All right. So when there's a prolonged impact time, the damage or the force on the bumper is going to be reduced, thereby creating or reducing the damage on the body of the car. So the application is what I've just explained here: vehicles, bumpers, airbags in vehicles, cushion in gymnasiums, helmets, shin guards. Of course, the footballers, they always have a shin guard, and at the back of the shin guard you have foams there. Okay, shoulder pads, etc. Absorb impact energy and reduce the magnitude of the force transmitted to the body. They prevent or reduce physical damage by prolonging the impact time and reducing the impact of force. Okay, these are what I've just explained. All right, let's quickly look at this question, guys. Let's quickly look at this question. All right, when taking a penalty kick a footballer applies a force of 30 Newton for a period of 0.05 seconds. If the mass of the ball is 0.075 kilogram, calculate the speed with which the ball moves off. Okay, quickly solve the question and let's see what the answer will be. Okay, I expect you must have finished solving the question now, but there's something which you must have to know. When you want to play, if a footballer wants to play a penalty, at that moment he places the ball on the particular spot. So what then do you think is the initial velocity of that ball? Of course it is 0, because at that spot the initial velocity, the ball is at rest, so the initial velocity is 0. So take all parameters, substitute, and you get your velocity of the ball, which is the final velocity v. Okay, so let's quickly dive into what Newton's third law of motion. Okay, for every action there is an equal and opposite reaction. Okay, so if you have a body 1 exerting a force on the other body 2, okay, the body 2 will exert an equal but then opposite force on body 1. So this Newton's law is referred as what Newton's law of motion. The law, to every action there is an equal and opposite reaction. Okay, so it simply says that the action that the forward force is equal to the reaction. The action is equal to reaction. Of course, reaction takes a negative sign because it is moving in the opposite direction. They are both forces, and remember, forces are vectors. So the negative sign shows the direction of the force in the negative direction. So mathematically, we have F force on body 1 due to body 2 is equal force on body 2 due to body 1. Remember, the negative sign indicates that it is moving in an opposite direction. Okay, let's quickly look at Newton's the application of Newton's third law of motion. Okay, after the application, we're now going to some solving of numerical problems. So the first one is jet and rocket proportion of jet and rocket proportion. So you agree with me that in jets the fuel in jets are actually mixed with compressed oxygen, so that by the time it is ignited, the gas in there burns. Okay, when it burns, when the gas is there is being burns, what happens there is that the gas inside there, of course, it has masses. Okay, so it is going to exert, it's going to produce much velocity. The gas is going to escape. It's going to be expelled with much velocity. Okay, so the mass of the gas is massive. At the same time, we now produce a great we now expel much speed as it comes out, as it's being expelled out of its nozzle. So together we have mass times velocity, giving you the momentum of the gas coming out of the aircraft. So immediately this momentum of this gas at a particular time, which is the force now, momentum per unit time, now hits or exerts on the ground floor. What happens? There's going to be a reaction of an equal momentum back on the jet. So when this happens, the jet begins to do what? Begins to find its way, or begins to make a forward movement. And that forward movement or upward movement is referred as as thrust. Okay? So that is what we have in this explanation, that the jets are aircraft, and aircrafts are used for transportation, military and other purposes. Rockets are used for launching of satellites, military and other purposes. Gases are burnt within the combustion chambers of the engine, as jets of the hot gases are expelled downward from the aircraft or rocket through the tail nozzle at a very high speed, and an equal and opposite force and momentum is given to the aircraft or rocket, which then moves it forward. Okay, so there's an equal and opposite reaction. The momentum from the expelled gases, okay, hits the molecules around the air or even the ground level, which propels the jet to move forward. Okay, so this is what I've just been explained. So let us look at some mathematical explanation to this. Okay, here we have the force of the rocket. We have the force of the rocket. Okay, and here we have the force of the gas. Both forces are equal, but this is negative because it's in the opposite direction. Remember, my force is what rate of change momentum with time. So m1v1 minus m1u1. So this is the change momentum of the rocket, initial momentum of the rocket, final momentum of the rocket with time. The same thing goes here, that the initial momentum, final momentum of the gas in the what of the gas, okay, final momentum of the gas minus the initial momentum of the gas with time. But then the rocket was at rest, so also where the gas is in there, we are at rest. So when you substitute u0 for u here and 0 for what u2 here, you are going to have m1v1 over t equal negative m2v2 over t. So let's look at this m2v2 concerning the gas in there. Okay, when you look at this, m2 over t, take note, m2 over t of the gas times v2. Now in this expression, m2 over t is given as the mass flow rate of the exhaust gas. Mass of the gas over t, mass per unit time, which is the mass flow rate of the what? Of the exhaust what? Gas. Take note of this, of the exhaust gas. That's the gas coming out of the what? Of the rocket. So that is the mass of gas expelled per second. And what is the unit? Kilogram per what? Second. So the thrust on a rocket, okay, is given as what? The mass flow rate of the gas times what? The velocity of the gas. Okay? But if you are given the mass and given the time, just key in the value of the mass and the time times what? The velocity. Or if you are given the mass flow rate, just quickly substitute the mass flow rate times that of what? The velocity of the gas to get the what? Thrust on rocket. Okay, here similarly, this is one of the application of what? Newton's law, that is the recoil of a gun. Okay, a gun is being shot, the mass, the bullet from the gun has a mass and it moves with a velocity v, and that of the what? Now when the gun is being shot, of course you are going to see a kind of what? An experience by the person that has shot that particular what? Gun, a kind of movement. So the person shooting that gun, the hand moves, of course the hand or the person has a mass m, and the gun itself has its own what? The gun has its own mass. The gun has its own mass. The bullet has its own mass. Then the bullet goes with a velocity v, and the gun itself moves with a velocity what? V. Okay. So, but in this case, there is a kind of counterbalancing of the mass and the velocity, such that the momentum of the gun is equal to the momentum of the what? Of the bullet. The mass of the gun, of course, is massive, is greater, but then its velocity is what? Is less. But the bullet moves with a greater velocity, though the mass of the bullet is less. So when you now multiply both of them, the mass of the gun and the mass of the what? And the velocity of the gun, it will give you the same value as the mass of the bullet and the what? Speed of the bullet. So for every action, there is equal and opposite what? Reaction. So we can apply this in solving questions as well. So we are going to have the mass of gun, okay, as we have here. The force, the action, the force from the gun is equal to the what? The force which the bullet used in what? Moving out. Okay, so right here we have m1v1, that is the mass, the final velocity of the gun minus the what? The final momentum of the gun minus the initial momentum of the gun with time. Then here we have the what? The final momentum of the bullet minus the initial momentum of the what? Bullet with time. But this occurs at the same what? Time interval, so they both cancel each other. Then we now have the momentum, the change momentum of the gun is equal to the change momentum of the what? Bullet. But at initial state, before the motion took place, the gun was at rest, so also is the bullet was at rest in the gun. So when you substitute u1 and u2, 0 for u1 and for u2 in the equation we have up here, finally we now have m1 v1 equal to what? m2 v2, meaning that the momentum of the gun is equal to the momentum of the what? Bullet. Negative sign, of course, indicates what? That the bullet and the gun moved in opposite what? Direction. Okay. So also the two-third law can actually be applied can aid in walking when we step our foot on the floor, we have exert a force, and there's a reaction force of the ground on the person. So it aids in what? In walking, in skydiving, drifting of balloon, being deflated. So quickly, let's jump into what these questions. Quickly, let's take the question. Number one says that an aeroplane has a total mass of 3,500 kilograms and aviation fuel of 6,000 kilograms. If the fuel is consumed at 180 kilograms per second, take note, you should know what that something is. 180 kilograms per second. I guess that should be the mass flow rate. What is the minimum velocity of the exhaust gases required to enable the plane to take off? So guys, quickly take your parameters, and let's see if you are right in the next slide. Okay, let's move to the next slide. Okay, fine. First and foremost, you have to note that the upward force, which we have here, is equal to what? To the weight of the aeroplane and the weight of the aviation fuel. But how can we obtain the upward force? Okay, we have that force, of course, is the rate of change of momentum with time. So we have the mass of gas, because the mass of gas that is being expelled from the rocket, that will create a reaction force, which is the thrust that will enable the rocket to move. So this is the mass of the gas, okay, over T. So that the reason why we have this mass of gas over T out here, this reason being that in the question we are given the mass flow rate, which is mass per unit time, and the mass per unit time is 180 kilograms per second. So the question we have to look for V, the velocity with which the rocket takes off. But then the initial velocity, because the rocket was at rest initially, so the initial velocity is 0. So the upward force now is 180 V. So what then is the weight of the aeroplane? Of course, weight is equal to mass times acceleration due to gravity. So the mass of the plane we have here times g, which is what we have here. We are taking g to be 10 meters per second squared. So we have the value 35,000 Newton. Same goes to that of the aviation fuel. The mass of the aviation fuel was given to be 6,000 times 10, which is 60,000 Newton. So let us substitute what we have here. Here, the upward force from what we have down here after this illustration is 180 volts. Then the weight of the aeroplane is 35,000 Newton, while the weight of the aviation fuel is 60,000 Newton. So when you now equate 180 V, add this to give me 95,000. So it means that to get my V, divide both sides by 180, and at the long run, I have my minimum velocity the rocket would have to take off, which is 527.8 meters per second. Number 2 example says a gun of mass 2.0 kilogram fires a bullet of mass 1.6 times 10 minus 2 kilogram due east. If the bullet leaves the nozzle of the gun with a velocity of 150 meters per second, what is the recoil velocity of the gun? What is the recoil velocity of the gun? Okay, so we have the question here. So quickly, guys, take your parameters. Okay, then fine. Then the first fundamental basis of equation we have here, or the principle of which this question is being deduced from, is that we have the recoil force, which is equal the repulsive force. Okay, sorry, the propulsive force. So the recoil force of the gun, we have the mass times acceleration of the gun. But here for the bullet, we have mass times acceleration of the bullet. But then what then is acceleration? This is mass. What then is acceleration? Change in velocity of the gun with time. Same also for the bullet, is the change in the velocity of the bullet with time. But this occurs within at the same rate or time interval. So we now have the time cancels itself. So we now have m into v minus u for the gun, then m into v minus u for the bullet. So since both of them were initially at rest, which is 0, substitute the initial velocity for 0. So you now have mass and velocity here. Okay, in this question we just substitute directly. Mass of the gun is 2, then the velocity of the gun unknown, then the initial velocity is 0. Mass of the bullet is 1.6 times 10 raised to power minus 2. Then the velocity with which it moves is 150 meter per second, but the initial velocity is 0. Okay, then when you open up a bracket, you have 2v, that is the velocity of the gun. Multiply this together, you have 2.4. So when you now make v velocity of the gun is equal to the formula, you end up having 1.2 meter per second. Yes, 1.2 meter per second. But where is the direction of the gun? It is due west. Due west. Okay, that is the opposite direction to that of the propulsive force of the bullet. Okay, guys. Now I would like you to go through this question and evaluate your understanding. Evaluate your understanding with the questions we have here. We have questions 1, 2, 4. I would like you to go through this question and you apply what we have studied from Newton's first law to Newton's second law. Basically, what we have here is in Newton's, mostly a question under Newton's second law of motion. So please look at the equation very well. Look at the formula. Force is equal change in momentum over time. Then when you cross multiply, you have force times time, which is equal change in momentum. So look at this question, go through them, understand the basic concept, substitute your values properly, get your parameters, substitute accordingly, and get your final answer. So guys, I wish you all the best. Keep studying and keep studying hard. Okay, and we have more other classes to take, or to more other contacts to have in this online tutorial. So the best of all, thank you and God bless. My name is Mr. Uche.